Sure, how about this? Let F be a field and let GL2 of F be the 2x2 matrices that are invertible with coefficients in F. And let's prove that the map that goes from GL2 to F cross to non-zero elements of F, of the field F, given by phi of a matrix is the determinant of that matrix, is a group homomorphisms from here to here, and describe its kernel. The very first thing we need to do is to show that that is a well-defined map, that when you take a determinant, you land here. Why is that? Because GL2F, as I said, is a set of invertible matrices, 2x2 matrices with coefficients in F, and if a matrix, a 2x2 matrix, is invertible, it's of this form, ABCD with ABCD in F, and AD minus BC being non-zero because of the formula of the inverse matrix of a 2x2 matrix. If you then realize that that is the determinant of that matrix, then GL2F are those 2x2 matrices with coefficients in F that have a non-zero determinant. So therefore, whenever I send by phi a matrix A and I get the determinant, by definition of GL2, the determinant will be a non-zero element, and therefore it is in F cross, and therefore the map is well defined. Next, let's show that it is a group homomorphism. So we need to take into account what are the binary operations that go with those sets. And in this case, GL2 is a group under matrix multiplication, and F cross is a group under multiplication in the field. And now we're taking determinants from here to here, and we want to show that that is a group hom. If it is a group hom, what we need to show is that phi of a product is the product of the phi's, that phi of AB is phi of A times phi of B for any two matrices in GL2. So how do we prove that? Well, phi of AB by definition is the determinant of the product of the matrices, and now from here to here you can show separately, or probably you know, that the determinant is multiplicative of matrices. So the determinant of a product is the product of the determinants. And now the determinant of A is the image of A under phi, determinant of B is phi of B, and therefore phi of AB is phi of A times phi of B, so it is a group hom. Finally, we want to describe its kernel. The kernel of a homomorphism will be those elements that are mapped to the identity on the target group. In this case is the 1 in the field F. So the kernel of phi will be those matrices, that the 2x2 matrices whose determinant is exactly 1 in the field, and those matrices are, well, those that have determinant 1. There is a special name for this subgroup, or this subset of GL2, and that's SL2, the special linear group of 2x2 matrices with coefficients in F. By the way, the fact that phi is a homomorphism automatically proves that the kernel is a group, so, or a subgroup, and therefore this is an easy way to check that SL2 over F is a subgroup of GL2.